Following is a demonstration of spatial downscaling using a multifractal technique. Suppose we have information at a coarse resolution. This information is not appropriate for crop models, so we need to downscale this information to a more appropriate and manageable resolution. In this demonstration, we're interested in statistical downscaling. Statistical downscaling is based on the concept of multiplicative cascades. A multiplicative cascade is the process of taking an initial value and then generating smaller pieces of that initial value based on some weights which are characterized probabilistically. So the result of this process is to obtain information which is now at an increased resolution. So at level 0 we had this resolution for the initial value, and then the size of these subdivisions is now smaller, which increase the resolution. We can repeat this process R times so that R is the scale or the level at which we desire the information to be. Therefore, putting together a statistical downscaling and a probabilistic characterization of these weights, which is given in a multifractal fashion, we obtain a multifractal downscaling technique. The multifractal characterization is performed to characterize the way the weights are generated. These weights are generated as outcomes of a random variable. Let's call it random variable W. In this demonstration, we are interested in a rainfall application. Okay, so we want to downscale information coming from rainfall measurements. Therefore, we require two random variables forming that random generator of the cascade process. So we need one random variable that generates the zeros of rainfall measurements. So the instance at which there is no rainfall. And we need another variable that generates values of rainfall at instance in which rainfall appears. So the probability of having zero rainfall is characterized by this model here, this piece here. And then the characterization of the parameters of the random generator for the times in which we have rainfall is this one here. These two things together form the beta log normal model. And the formulas for the two parameters of the random generator are these. And they are based on the fact that the information to be downscaled is log normally distributed. Now we are going to apply this downscaling procedure to a grid of information in the Andes Plateau. We have in this area a set of stations distributed over all the area so that we can validate the method in this heterogeneous terrain. The nature of this grid of information is rainfall, and this rainfall is obtained from the Tropical Rainfall Measuring Mission. We have data starting in January 1st of 1999 until December 31st of 2006, and this information has resolution of about 28 kilometers, which is too coarse for our application. Therefore, we want to downscale this information to about 1 kilometer resolution. More detailed information about this downscaling procedure can be found in this recently accepted paper in the Journal of Nonlinear Processes in Geophysics and entitled Spatial Random Downscaling of Rainfall Signals in the Andean Heterogeneous Terrain. SIP has developed a software package in MATLAB for spatial downscaling using this multifractal technique. We will proceed by running a demo of such a package. First thing we have to notice and to give to this software package is the area under study. So this is the Andes Plateau. It's part of Peru, part of Bolivia, and here are the stations to be used for validation. As it can be observed, the stations are distributed over all the area so that all heterogeneous types of in the area are taken under consideration. As we mentioned, the first thing to test is the log normality of the data. So let's take this TRMM in image. And run through it a normal probability test. Why a normal probability test? If this data is log normal, we can transform it into normal information so that we can run this test, and then we can transform it back to log normal information. We observe that log normality holds for this specific snapshot. However, we know that this is going to hold for all the snapshots in the from January 1st of 1999 to December 31st of 2006. In order to preserve the heterogeneity after the downscaling procedure, so we need to correct the data with the following mask. Okay? This mask has been obtained as a result of taking the station's information and interpolate between them using the elevation map. For such a task, the software Unscreen was used, so that we obtain information at the desired final resolution. With this information, we can correct the downscaled data out of TRMM information. But in order to do that, we have to be sure that this data is also log normal. So we applied exactly the same test. So we observe that log normality holds for the desired range, for the same range as it was held for TRMM information. Okay, so the next step is to test for multifractality. Testing for multifractality is just plotting the moments of the information initially for the same image we use for the log normality test for a TRMM snapshot, and then we plot these moments with respect to the scale at which these moments have been computed. If this plot is linear, then we have a sense of multifractality of this information. And we can test this assumption for all the moments. If linearity holds for a moment in particular, then we can assure that this is the range of moments under which we have multifractality. We proceed to apply the exact same test to the heterogeneous mask that we previously shared. Of course, we have now more scales, more resolutions to test. And we observe that linearity also holds to all these resolutions. And we have tested this for all the moments that we use for TRMM information. What this tells us is that we can use a multifractal characterization of the random generator that we are going to use for downscaling TRMM information. The next step is to compute those parameters using the formula that we use after characterizing the random generator in a multifractal fashion. Here, we just show several computations of the parameter beta for several snapshots in terms of the daily TRMM mean at that particular snapshot, or at that particular corresponding to that particular snapshot. And we observe that it fits the empirical curve defined for the parameter beta, which is the one obeying the following information, the following equation. We repeat the same procedure for the parameter sigma, and we observe the similar results, although the sigma parameter it's a little bit more spread out with respect to the fitting curve. We can now proceed to do downscaling of here MM information. So for that we pick the following matrix of information, which is at 28 kilometers. To this image corresponds the following heterogeneity matrix, which is at 0.875 kilometers resolution. We compute the values of beta and sigma, and then we proceed to do downscaling, and we obtain the following matrix of information at 0.875 kilometers, which is the same resolution as our heterogeneity matrix. So we are going to weight all these values with respect to this mask. This is the final outcome of this correction procedure, and this is the information that we are going to validate against the information of stations. So we pick a point. In particular, we are going to pick a point in the matrix of information in which Munani station is located. And what we do is we are going to construct the excellence probability plot of the data measured at that station and the data generated by the downscaling procedure. We plot these two together and we find that there is an excellent match for these two plots. Even more, we compute the confidence interval in which this generated data and this observed data should be, and we find that we are well into that confidence interval. We also plot the quantile graph of the generated data versus the observed data, and we find a very good agreement. So let's quantify the goodness of fit of this excellent probability plot, and also let's compute some statistics of the time series generating these two plots. So the software package also compute all these statistics. So we compute the Hurst index, the mean, the minimum, the maximum, the skewness, 3 quantiles, and all these measures of goodness of fit for the excellence probability plots. We observe that most of these statistics agree with the statistics of the generated information. The only main difference that we may find here is the one for the maximum, and that can be related to the fact that the downscale information is at about 1 kilometer resolution, whereas the information at the station is punctual measurements, which is assumed to be 1 kilometer resolution too. So with that, this demo is concluded, and we thank you for your attention.